Good morning. This is where we left off. And we finished this a little fast last time, so I wanted to go back over it. There were some what I call hot spots in the solution of this that I think definitely merit your attention. Number one, in order to apply, even if you remember the arc length formula, if you can't take the derivative of stuff, right? So, gotta, those are the, this was the chapter 5, transcendental function derivatives. Our second quiz, right? They come up over and over, and what they're going to do be in a case like this, it would be a complete stop if you can't take that derivative. You can't even, right? So that's why I make such a big deal out of derivatives. That's one reason I make such a big deal out of derivatives. The other thing is you can't get antiderivatives if you don't know what a derivative looks like, because whenever you get when you get an antiderivative, it's the function whose derivative is what you started with. And if you can't recognize the derivative of your antiderivative, that's a problem. Okay. So that's one hot spot here that I would absolutely, I've been screaming about the whole semester. So anyway, number one, this is our function. We got to take its derivative. All right, and so we'll go over here, and the derivative of the natural log of something is the something in the bottom, its derivative in the top. The derivative of secant is secant tan. So right there, there's two transcendental derivatives you had to know. You had to know the derivative of natural log. You had to know the derivative of secant. Boom, boom. Without that, you can't get started. Right? Essentially, it's 5 points blank on a test. Right? So learn those derivatives. The second thing is, once we got the derivative, it turned out to be tangent. We plug it into our formula for our bounds. We've got to integrate what's left. Now, or the book won't give you something that you shouldn't know how to integrate. But it's got to be within the realm of stuff we've had, and you got to know the stuff we've had. So right here, we wind up with 1 plus tangent squared. You got to know secant squared. Right? The basic trig formulas you have to know. No, there's just completely non-negotiable are cosine squared theta plus sine squared theta is 1. Fundamental identity of all trigonometry right there. Right? And then if I divide through by cosine squared, here. Right? From that identity, we're going to divide through by cosine squared. To get another identity, cosine squared divided by cosine squared is 1. All right. I'll say calor. It's hard to believe I'm saying that. It's below 0 outside. these radiators in here. And so cosine squared over cosine squared is 1. Sine squared over cosine squared is? What?
Sine squared.
Sine squared divided by cosine squared is? Tangent squared. 1 over cosine squared is? What trig function is 1 over cosine? What trig function is 1 over cosine?
Secant.
Secant. So this is secant squared. Then with this guy, same formula. Divide through by sine squared this time. And we have cosine squared over sine squared is cotangent squared. Sine squared over sine squared is 1. 1 over sine squared is cosecant squared. So those three are our fundamental trigonometric identities. So those three are the fundamental trig identities. And there's times you're going to be using them in this direction and in that direction. In the case we just had, we used it in this direction. We wound up with 1 plus tangent squared under the radical. And right here, you can't proceed unless you know that's secant squared. You're stuck. Your problem ends right there. Unless you know that that's secant squared. So that's hot spot number 3. Lots of hot spot, you know. Hot spot number 1, right here. Number 1 is here. Right. Number 2 is here. Hotspot number 2. Hotspot number 3 is here. Once you have square root of secant squared, which goes to secant, the third is how do you integrate secant? You need to know the antiderivative of secant or how to get it. Now here I showed you how to get it. Either that or you can just remember that the antiderivative of secant is log secant plus tangent. Because by multiplying by secant plus tangent top, secant plus tangent bottom here, you wind up with something on the bottom whose derivative is on top. So either remember that trick and how to get it, or remember the derivative of secant. If not, your problem ends right there. You see what I'm saying? Every one of these are a hurdle. All right, and then number 4 was you plug in pi over 4, evaluating those trig functions from here to here. That was a little slow last time. It's okay if you don't remember secant pi over 4 off the top of your head. What you need to know is how to get it. How to get it. The unit circle. The unit circle. And I mentioned that the unit circle is on the back of the formula card that is in the front of your book, right? Right there, lots of trig identities there. You're going to need to know, by the way, several other trigonometric identities for chapter 8. More than we've already done. And you're going to have them because they won't be given to you on tests. You can put them on your formula card for the final. Right. So you've got to know how to get tangent of pi over 4, secant of pi over 4. I don't have those memorized. I genuinely do not. But I know that secant pi over 4 is 1 over cosine pi over 4. In fact, here's what I can do. I'm going to put an extra explanatory step in that we didn't have time for last time. From there to here, down here. All right. So suppose you're stuck on those. Suppose you're stuck on those. What do you do? And I'm sorry, you'll have to squeeze this in somewhere, but you're going to do this. That's natural log, absolute value, 1 over cosine pi over 4. My plus tangent is sine pi over 4 divided by cosine pi over 4. So you break them down into their components. Break them down to sines and cosines. Now, sines and cosines of the unit circle, I know. And the way I do it, I kind of don't have them memorized either. By now I probably do, but I use triangles. I use 30, 60, 90 triangles on the unit circle. I don't. This circle, I do not sit down and memorize that. The unit circle. I use 30, 60, 90 triangles. So I say, if I have, I'll show you. I'll show you when I go to evaluate those. Then here, minus natural log 1 over cosine 0 plus sine 0 over cosine 0. Okay. So right there was a hot spot. Right? So going from there to there and going from here to here. Then a fifth hot spot. Once you get this in here, do you know enough about logarithms to know that this whole second one is 0? Because the first one, 1 over cosine 0, cosine of 0 is 1, so that's 1 over 1. This is sine of 0, which is 0, divided by 1 is 0. So the inside the absolute values goes to 1 plus 0. The natural log of 1 is 0. Is that this one right here? Number 5. This one needs to be simplified, right? And I said I would. I kind of skipped a step, but here last time as we were at the end. This is going to be natural log. Invert and multiply here on this one. Invert and multiply. You're going to get natural log 2 divided by square root of 2 plus 1. This equals 2 divided by square root of 2. You invert and multiply. What is 2 divided by square root of 2? Don't leave it like that. That's square root of 2. 2 divided by square root of 2, well, 2 is square root of 2 times square root of 2. The numerator is the square root of 2 times itself, divided by square root of 2. One of those cancels, and that just gives you square root of 2. So I think we have,
It's not 2 square root of 2.
2 divided by square root of 2? No, because the 2 in the top, 2 divided by square root of 2, the bottom is just stays the same. The top, 2 is square root of 2 times square root of 2. The square root of 2 is what you have to multiply by itself to get 2. So 2 equals the square root of 2 times itself. One of those cancel, and it just equals square root of 2. And that goes there. Hotspot number 6. All right, so without trying to discourage you too much, lots of soft areas there. Lots of soft areas there. Some of them are not new soft areas. Some of them were the first week of class soft areas that are still soft areas, and that is concerning. That is concerning. All right, so lots. Every one of these are different. Like here is chapter 5. Here is high school trig. Yeah, pre-calc, exactly. Right.
Okay, so what I remember is when you have 2 divided by square root of 2, you multiply bottom and top by square root of 2.
Okay, good, good,
Bottoms
perfect,
cancel.
perfect, perfect, perfect. So your way works. So we have 2 divided by square root of 2. He's saying multiply by square root of 2 over square root of 2, right? Well, that's 1. That's a perfectly good way. So what do you get on the top? 2 times square root of 2. What do you get on the bottom? Square root of 2 times itself.
Square root of 2. Sure.
Okay. All right. Either way is fine. Either way is fine. All right. Okay. Some work to do here. Okay. All right. Go and get to work on this. Go get to work on this. This right here is basic. Oh man, let me just basic. We're gonna get be getting into so many more trig identities coming up. All right. And I think I've done this before, but I'm gonna do it again. Let's go to now here. I'm gonna show you something. Let's go to chapter 8. I'm gonna show you what you're gonna have to be doing. The next chapter. Not to mention the rest of this chapter when you run into a problem like that. I picked a random slide. Totally random. I did not look at the slides at all. All right? You see what I'm saying about trig? You're neck deep in this stuff. You're neck deep.
Secant cube.
Yeah, secant cubed is a sweetheart. Okay. To integrate. We don't have to integrate secant cubed here. Secant cubed will keep you busy a while to integrate. Now this, this you don't have to integrate. This is what it integrates to. But yeah, secant cubed. Now here, let's there we go. There's some more. More. Oh. Every single problem Now, I picked a random slide and I'm just starting to go. I didn't look for the worst. Okay. That right there is more here. There you go. This one. This is the easiest one. Case 1, non-repeating linear factors. This is the easy case. There's 4 cases. All right. And it's that and the next slide, all that. Nothing but cosecants. So here you go. Cosecant. You have to integrate cosecant. That's like the integral of secant, except it's negative log cosecant cotangent. You either need to know that or know how to get it. It comes up all the time. All right. Yeah. Now look at this. That integrates to that, but now you have to substitute back in because this is trig substitution is what this is. And over here, you see this trig over here? Your basic right angle trigonometry, you got to know ice cold. I'm not trying to scare you. I'm just saying this is what the prereqs are. Next one, repeated linear factors. This is case 2. All right, that one was actually pretty short. This one, okay, that's a shortcut. There we go. You're going to be doing this in like 3 weeks. 3 weeks. That one's short, actually. There we go. Trig sub, another trig sub problem. But you don't start with that. It starts like this. That's what they start looking at. I just did the problem 2 different ways. Right. I'm skipping that actually. Tells you, oh yeah, well, you get a bunch of them. Yeah, I'm not gonna get into this. So all I'm trying to do is showing you, I'm trying to just light a fire. Okay. This needs to be on the outside, and this right here, every one of these yellow spots is a stopping point. If you don't know how to do it, your problem ends right there. That's it, as far as you can go. As far as you can go. All right. So every one of these, I look at these here, I've told you before, they're like blades on a Swiss Army knife. Right? Why do you carry a Swiss Army knife, Mr. Milks? I've worked in Sac Hall for 18 years, that's why. This building always has something to fix. Okay. But okay, oh, this time I used that one. Oh, I needed this one. Oh, the little pair of pliers. That's good. You need to have the pair of pliers. Boing, 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 right? And then this little gizmo in the back. All right. You never use it, but when you use it, it's the only thing that works. Well, the next problem doesn't need that one or this one. It needs the Phillips screwdriver, the pliers, and a magnifying glass. This is what you're putting together is a set of tools. The trigonometry is a tool. The derivatives are tools. Right? And they're tools that help you build something bigger. Right? Moving on. Let me help you in this, by the way. Let me help you in this. I was in the library last night till 9:45. This part. I don't like staying at night. Because I'm an old man. Here's some love for you. Oh, yeah. Here's your nice, clean answer. Isn't that a nice, clean answer? That's a nice, clean answer. Okay. A surface of revolution. Now, up till now, we've been dealing with volumes of revolution. How do you get the volume of inside something, right? We're now going to get the surface area around that. The surface area of that volume, not the volume inside. Okay. And so you're going to have an axis of revolution, just like the volumes, and you're going to be revolving some function. All right? Now, you got to know these. That's the bad news. The good news is they're very similar to what we just did. What do you mean? This is big S. Remember what little s was? Little s was the arc length, right? That was integral a b square root 1 plus f prime of x squared dx. This was arc length. Now notice here how you see the length of that arc from A to B, the length of that arc. Now this is a straight line, but if that were wavy, the length of that arc determines the surface. If it's a straight line, it's going to have one surface area. But if that were to go like this between there and there, that would probably create more surface area. Right? See what I'm saying? The point is, it's related to arc length. That surface area has everything to do with the arc length. Now, you don't have to understand that relationship, but you do have to know these two formulas. You do have to know these two formulas. Now, what's the difference? This is the length of that arc across the top. And then you have 2 pi r. R is another radius function. Most of the time, it's the same as f, except when it isn't, right? Except when it's not revolved around an axis, right? Now, so you see that little s right there? The big S is 2 pi r, that r times the little s, because this is the same. These can actually be easier to integrate. Why? Because you got stuff on the outside of the square root. What made the other ones tricky, in particular, is you had that square root, junk under it, and nothing on the outside to be the derivative of the inside. You would like stuff on the outside that you can turn into the derivative of the inside. Right? I know what you're thinking. It just keeps piling on. It's true. It's true. Nice, easy one to start with. Not bad at all. Question: what? You don't have to, but what does that even look like? What does that look like? Well, it's 1/3 x cubed. Okay, so x cubed looks like this. And it goes through the point 1, 1. Minus 1, minus 1. That's y equals x cubed. 1/3 of that is a compression. It compresses it toward the x-axis, right? So you have x and y. So 1/3 of that, all these points go 1/3 the distance. Okay. And you're rotating that from 0 to 2. So 0, obviously here. 2 is right there. And so you're rotating that. You're rotating this stretch right here. About the x-axis. And so that's going to form what? A little trumpet. Yeah. And we're finding the surface area of the little trumpet. Okay. You don't need to graph that to do this problem, but I think it kind of helps, right? Question, how do you start? What is R here? This R, I told you, R of X is the distance between the graph of F and the axis of revolution. So when you're revolving around an axis, R of X equals F of X. Note. I should add this. When revolving y equals f of x about the x-axis, r of x just equals the f of x. And the same for r of y. When revolving, x equals g of some function y about the y-axis, r of y equals g of y. Okay. I want to add that. I think I'm going to add that to the slides. So here, big S is for surface area, small s is for arc length. It's going to be 2 pi integral A to B. There's A. It's B. R of X. It's just a function. Square root 1 plus the derivative squared. So over here, f of x is 1/3 x cubed. F prime of x is x squared. So I'm going to have x squared squared. And right there is f prime. Dx. So the square root part is exactly like the functions or the problems we just worked for arc length. What you have new here is the 2 pi and the r, 2 pi r. And 2 pi r gives you the slice. It gives you the area of that band, actually, not a slice. Do both of you understand the setup?
Why is it y x squared? Okay.
Well, yeah, because you have x squared, it's squared. So you're going to have this 1/3 can come out. Or get ready for a pop quiz. Ready for a pop quiz, right? Shake your head. Please tell me you're ready for pop quiz. Okay, yes. Okay. X cubed. Pop quiz. How do you integrate that? I'll give you a hint. Back to where we just came. No, not that one. This one. Right here. You have a function to a power. On the outside, do you have its derivative or something that can be made into its derivative? This is a U sub problem right here. U substitution. Ready?
The Bachelor is
No, I don't want that. Ready? That is so cool. Oh, I like it. Me gusta. Just like before, that is U. What is du? Du is 4x cubed. Is du. Dx actually. So I have an x cubed dx. I need a 4 there and a 1/4 out here. I'm not even changing over to u's, but if I did, that's what we do. Generally, let u be what's under the radical, just like we did on the other one. Get what du is. Just so happens you got an x cubed sitting fat, dumb, and happy right there. That looks like me on my couch right there, just ready to have something fall upon me or something. Okay. 4, you need a 4 though, because du is 4x cubed dx. 4 there, 1/4 out there. Rather than switching over to the u's all the time, this is what I do. All right, so now I have a function to a power. This is to the 1/2 power, right? Times its derivative. So this is going to be, what am I doing? All right, so we're going to have this is going to be pi over 6 time to integrate. This is to the 1/2 power, right? So I'm going to raise it to the 3/2 power. I'm going to divide by 3/2, which is the same as multiplying by 2/3. Dividing by 3/2, same as multiplying by 2/3, and that gets integrated from 0 to 2. So that's going to be pi over 9. This, plug 2 in, 2 cubed, 2/4. 2 to the 4th is 16, right? 16 plus 1, 17. Plug in 0. I get 1 to the 3/2, which is 1. Right. Any questions? Now, whenever I ask, are there any questions? Let me tell what I'm really asking. Could you do one exactly like it right now? Yeah, okay. All right. That's what I'm asking. But I usually go back through. I go back through almost every example, right? Number one, you got to remember that formula. The good news is it's very similar to the arc length formula, right? That one. Very similar. You have 2 pi r. And think of it, it's revolved. So it's the line on the outside and it's revolved. Whatever the curve is, the length of that curve, and then times 2 pi r, right? Whenever you're revolving around the same axis as this, that, by the way, it has to be the same axis, right? This is a function of x revolved around the x-axis. If not, this technique does not work. You'll have to play with it to make it revolve around the same axis. So if this were around the y-axis, what would I do? If that were around the y-axis, I would solve for x over here. So you have x as a function of y around the y-axis. And I would apply the same technique. Because then I'd have an ry, a g of y. Find the surface area of a cone.
How do you got the 2 over 3?
Oh, right here?
Yes.
Well, when we integrate this, this is to the 1/2 power. Here, I'm going to add one more. That is going to be this is that. I just took away the square root sign. Right? I put it to 1/2. So now I have a function to a power times its derivative. This is u substitution. So this is u to the 1/2 du. So I take this to the next higher power. That goes to the 3/2 power. And I divide by 3/2, which is the same as multiplying by 2/3. And guess what? It's about time for this to crash. What do you think? Here's 53. I like that. I like it. That's cruel and unusual. Right? Okay, so added 1 divided by the new exponent. A little bit of simplifying out here. You plug in the 2, you get 17 2/3. Plug in the 0, you get 1. Cone of height h, radius r. Now we did the volume of a cone with the disk method, shell method, one of those, right? I think, in fact, I think it was one of the first disk method problems. Right. So what do you have here? We have a that revolve. That is h. This is r. Do that and redo it. So I'm going to do that here. This. Okay, right. So I have my cone. I know my formula, right? big S is 2 pi integral a to b. The radius function, r of x, times square root of 1 plus f prime squared. I need my function f of x. What is f of x? It is the function that is revolved. So this buzzard right here is f of x. What is that? Now we did this. We did this back for this method. What is the equation of that line right there? And this is a case that if every single day, my advice to you is to go over your class notes in detail. Just plow through the examples and work a few problems. That's where the 2 hours per class period comes in. But this is going to be a function that has slope what? It's a line through the origin, so it's y equals mx plus b, right? B is 0. The y-intercept is 0. So what's its slope? Rise is h, rise is r, run is h. So this is going to be rise r over run h x.
That was easy.
Okay. If that's f of x, f prime of x is r over h. Okay. So S 2 pi integral from A to B. My A here is 0. My B is H. What's my radius function? So you got some blanks to fill in here. R of x. Then we're going to have square root 1 plus right here. That's f prime of x. Fill in the blank. Fill in the blank. What goes there? R of x is just my f of x. R over h, like I'm going to put it in green, times x. This is just r over h. This one's actually easier than the last one. Maybe I should switch these. Yeah, I think we're going to switch. Yeah, this is easier. So, of course, that doesn't switch in your notes, but sorry. Okay. We're all set. Proceed, right? Now, my personal philosophy is I bring everything past the integral sign that I can. What can I bring past the integral sign? Factors that don't depend on x. Factors that don't depend on x. So for example, you see that r over h sitting right there? The x has to stay in the integral. R over h can come out. So this is going to be 2 pi. R over h can come out. What about this? That radical doesn't even have an x in it. That radical is a constant. You're supposed to go yabba dabba doo. All right, so that can come out. What's left in? What's left inside the integral? Integral 0 to h, just an x. Is that amazing or what? What looked so complicated just collapses. Now, we can simplify this out here. So we're going to go 2 pi r over h. This radical, that I can make the h, or excuse me, the 1, I got to get a common denominator, right? H squared. So this is h squared divided by h squared. All right, so I'm going to have a radical h squared plus r squared divided by h squared. So that's what the radical becomes. This guy becomes a x squared over 2. The antiderivative of x is x squared over 2. So I'm going to have an x squared. I'm going to put a 1/2 out here. 0 to h. Now, are y'all numb? Just very, very content. Is your soul in harmony with the universe here? Is that why your soul not in harmony? Huh? You have a question? You know I'll answer a question. Especially for my 2 favorite students in the class. Hey, you waged your whole life to be one of the the teacher's 2 class pets, right? Yeah, we're used to the radical being the hard part. And the radical is a big fat constant. It comes all the way out. It doesn't have any x's in it. The only x is that one there. So now,
Why h2 divided by h2?
oh, that's what 1 is. 1 is h squared divided by h squared. I got a common denominator because I want to add those. Right? So to add those, I need a common denominator of h squared. So I wrote 1 as h squared over h squared. So that means the bottom is h squared. The top is h squared plus r squared. So I added fractions there. The cool part now is that this becomes that's a perfect square in the bottom. You see that h squared in the bottom? That's an h, right? So this is going to be pi r over h square root h squared plus r squared over h. Times h squared minus 0 squared.
You don't cancel the h2 and h squared and h squared?
These two?
Yes.
No. No. I say dolor. No. Oh. Okay. Time for a fraction review over here. Here, ready? So if I have, let's say, 3 plus 5 over 3, right? I got something plus something else divided by the something right here. That, so 3 is the same top and bottom. I'm using a simple example. This really equals 8/3. Right? However, 3 plus 5 over 3. If I cancel the 3's, equals 5. Right? That one is yeah, so no. You can't cancel those. You can only cancel factors. So if h squared were a factor in the top, multiplied, in other words, by the whole top was multiplied by h squared, then I could cancel. But right now, h squared is a term in the top. It's added. Well, look at what happens here. You ready? This is an h squared. That's a 0, of course, right? So this h squared cancels with those two. That's h times h. That's h squared in the bottom. There's an h squared in the top. So that whole thing equals pi r square root h squared plus r squared. Graphite to paper, lots of graphite to paper. It doesn't make you feel any more comfortable, but I had to do it because I goofed off in Calc 1 and Calc 2. Well, I goofed off in Calc 1, got my head handed to me in Calc 2. So, yeah. Back up. This is the heart of the beast over here on the right. Why is it the heart of the beast? Because that helps you set up this. To me, it's very hard to do that without this. So you set up what a cone is. A cone is a line segment revolved around the x-axis. Right?
How is h equal to 0?
Oh, you know what? That h equals b. That's a b. Good question. Right. A to b are my bounds of integration, a to b. So that's a b. Okay. I'm glad you asked that. Did you think that was a 0 too?
I didn't even notice that.
Oh, okay. 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 All right. So I start graphing a cone. I got two things backwards here. This is bugging me. That's not right. It's supposed to be like this. Then solid out to there. Other way around. So that dark blue line segment is what gets rotated. So that dark blue line segment is what we need the equation of. That dark blue line segment. That's what gets rotated to make the cone. It goes out to h. It's h this way and r that way, the radius, right? What else? If you rotate it, this becomes our function, rise over run, no y-intercept, right? Well, it does have a y-intercept, it's 0. And its derivative is r over h. So I plug the derivative in where the derivative goes, right here. Square it under the radical. My radius is the function. Right? And a to b, 0 to h. That's the 0 to h. Again, if this were a 5-point test problem, that would probably be worth 3 points right there. believe it or not, the algebra was harder than it looked, but it's not real hard, but you do have to simplify it. If you want to simplify something under the radical, try performing the operation. So when we perform that addition, you wind up with a square, a perfect square in the bottom, and that perfect square becomes an h times an h over here, cancels with that h squared out there. And all you're left with is pi r and that radical. Now radical is a constant, because when you're given the cone to integrate, you're given the height of the cone, h, and you're giving the radius of the cone, r. You're given that in the problem. So you're going to expect to have h and r in your answer. What you can't have in your answer is x. Let me see, this looks familiar. Gabriel's horn, one of my favorite problems in all of math. This is, you'll tell your friends, right? This is fun. I have this. What I use for lecture notes is a lot of times just slides from the previous semester, right? And I had a student missing that day. Do you know Elizabeth Higgins on campus? Right? Well, she was missing that day. So I put a happy birthday slide in the slides, right? To see if she would see it, right? Because she's supposed to review the slides when you're not in class. I'm not going to say what she did. That gave me a little sticker. Okay. Gabriel's horn. Whoa, we're missing a. Whoa, we're missing a. I'm missing the slide. I'm missing the slide. Okay. Well, we're going to do Gabriel's horn, and we'll do that. Okay. So Gabriel's horn. What is Gabriel's horn? You have the function y equals 1 over x revolved around the x-axis from 1 to infinity. So what that looks like is this. It's this section from 1, 1 to infinity, right? And it's revolved around the x-axis. So it looks like this. So that's the horn. Question. Find its surface area and volume. What is its surface area? Well, this is f of x equals 1 over x. You're told that. Pop quiz. F prime of x equals what? You guessed it. Derivative of 1 over x. F of x, 1 over x, that is this. So its derivative is minus 1 x to the minus 2. Bring the constant, the exponent down front, Subtract 1 from the exponent. That is minus 1 over x squared. Please tell me you both got that. I don't want to hear. I don't hear that. I don't hear anything. I hear nothing. Why do you need that? S, big S is 2 pi. Integral. Here's a little bit tricky. You're not responsible for anything like this. You're not responsible for anything exactly like this, but what are our bounds of integration here? Our bounds of integration are from 1 to infinity. So it's 1 to infinity. Now, we haven't had infinite bounds on integrals. Or have we? I don't think we did that yet. But what's my radius function? My radius function is my function. Right? 1 over x. Then I have the square root. 1 plus the derivative of the radius function, in this case, squared. So that's minus 1 over x squared dx. Any question on how to set that up? That you should know how to do. We're going to get to a few things you're not expected to know how to do here. Okay? But, watch this. 2 pi integral 1 to infinity 1 over x square root 1 plus 1 over x to the 4th dx. Very cool. Once again, just like the h's we did, you remember the h squared that you just asked about, Jesus? At 1, I'm going to write as x to the 4th divided by x to the 4th. I'm going to perform that operation in there. That's 2 pi integral 1 to infinity 1 over x square root x to the 4th plus 1 divided by x to the 4th dx. That equals 2 pi integral 1 to infinity 1 over x. The denominator is x to the 4th. So that is square root x to the 4th plus 1 over x squared. That's a perfect square. Okay. This is going to be 2 pi integral 1 to infinity 1. Okay, this is got x times x cubed. X times x to the squared, excuse me, is x cubed divided by square root x to the 4th plus 1 dx. It turns out we haven't had the technique necessary to integrate that. So you're not responsible for this integral. I know what you're thinking. That's 1. But what we're going to do, we're going to cheat. Is that this integral, since it's got a plus 1 in it, is bigger than
why is squared x squared?
because it's the square root of the x to the 4th in the bottom. gives you x squared? Good question. 2 pi.
So on that part, you can't.
So that's the square root of a quotient is the square root of the top divided by the square root of the bottom. The square root of x to the fourth is x squared. That combines with this x gives you x cubed. Now what I'm doing here is I'm canceling off this 1 right here. If I cancel off that 1, I get a smaller integral. You'll see why I'm doing that in a second. We got 2 minutes. Okay. So this is going to be 2 pi integral x squared in the top, x cubed in the bottom, dx, 1 to infinity. That is 2 pi integral 1 to infinity, 1 over x dx. Now we haven't talked about this infinity part yet. But the way you handle that infinity right there is you do a limit. So this is going to be 2 pi times the limit as k goes to infinity of the integral 1 to k 1 over x dx. So that infinity becomes a k, and we take the limit as k goes to infinity. What's the antiderivative of 1 over x? If I had 30 seconds, I'd play my jingle and do a pop quiz. Right? I'd do that again, right? So this is going to be 2 pi limit k goes to infinity bracket. The antiderivative of 1 over x is natural log of the absolute value of x. Okay. This is 2 pi limit k goes to infinity bracket natural log of k minus natural log of 1. Natural log of 1 equals 0. The natural log of k as k goes to infinity is infinity. Remember, because the natural log function looks like this. This is y equal natural log of x. As x goes to infinity, the value goes to infinity. So that this part goes to infinity. So the whole integral is infinite. Up here where we did the greater than, we showed a smaller integral was infinite, so our original integral has to be infinite. Right? We don't have time today, but we're going to do the volume. In the meantime, that first slide, in fact, today, you need to be looking through those slides of today. And when you find hot spots, go do something about it. Come see me. Do a YouTube video if you need help. Right? Go back and listen to the video in class for the explanation. See ya.